So there are several different reaction types. We'll talk about a few of them today and do a few more tomorrow. So you can recognize patterns and reactions, and this will help you predict what will happen in a reaction and help plan, for a certain product that forms. So for the first one, synthesis. Have you heard that term before, synthesis? Photosynthesis. Okay, so not exactly change. I mean, there definitely is a change in these reactions, but it doesn't actually mean change in this context. What would it mean, synthesis? To synthesize something, what would that mean? So they meant synthetic, right? Like they meant that term. Like synthetic does mean man-made. But when you synthesize something or make something synthetic, you are creating something. You're bringing things together. So synthesis means to bring things together. That's right. Yeah, making sugar out of light. And so you're bringing things together to create something new. So it's two or more different things that combine to make one new compound. Two or more substances that combine to produce one new substance. So this is important, two or more to produce one. So general way to write this would be substance A plus B goes to form substance AB. So you have two separate things, A and B, and they combine to form one new thing, AB. So you could have something like this. You have Fe combine with chlorine gas to produce iron chloride. Now you balance this, you got 2 in front of there, 3 in front of the Cl, and 2 in front of FeCl. So this would be A right here, this would be B. And so you have two different things. Now, even though you have a total of 5 on this side, you have 2 molecules of Fe, 3 molecules of Cl2. You have 2 different kinds of molecules. So that's what we mean when we say 2 or more. We have 2 kinds, and that goes to form one kind. So even though you have 2 molecules of FeCl2 on the right-hand side, you only have one kind of molecule, and that's what they mean. You have 2 kinds going to one kind. So that you can add to balance equations. These are called coefficients. And that would be used to make sure you have the same number of atoms on both sides. Because if you didn't have this right here, but you had it on that side, what this would be saying is that you have one Fe atom going to form 2 Fe atoms. So you can't create atoms out of nothing. You can't destroy atoms or create atoms. So if you start with 2 Fe's, you have to end with 2 Fe's. Same thing with Cl. You have to make sure the number of atoms is balanced. I think you missed that day in class, but it's due to, we can't create matter. We can't make atoms. We can't destroy atoms. So atoms can be rearranged. You can break the bonds between these atoms and rearrange them, but you have to make sure that they're balanced. So the way we balance it would be to put numbers in front. Now, we can't change the bond number though. So we couldn't, if we want 6 Cl's on this side, we couldn't just put a 6 down here. Because even though you do have 6 Cl's on both sides, this means something different chemically. This is a totally different compound than Cl2. We learned before about this, about how you have O2 and you have O3. O2 is what we breathe in. O3 is ozone, that's poisonous to us. So by changing these subscripts, you change its identity and how it acts. And so we can't change these numbers down here, but we can put numbers in front to balance the equation. Does that make sense? Okay, so that is the first reaction type. One more example really fast before we go on to the next reaction type. You could have something like this take place too. So this is an element in an element down here. I'll write that down here first. So you can have an element reacting with an element. Where it's just one kind. You know, it's just Fe, pure iron, pure chlorine, reacting to form a compound. But you could also have two compounds reacting to form one compound. And so you could have this, where you have CaO, calcium oxide, plus water. Goes to form calcium hydroxide. So in this situation, you have a compound and a compound. So this one compound right here, CaO, reacting with another compound, water. But it's going to form one compound. So once again, you have two different things forming one thing. So that's also synthesis. Whether you have two elements or two compounds or one element in a compound, if they form one thing at the end, then that's synthesis. So that's the first reaction type. Second reaction type is combustion. So that's when you have oxygen combining with something else, and you always see a flame. So combustion, you would think of it as, you know, say explosions, but it really just means fire. It means something's burning. So oxygen combining with a substance, it releases energy in the form of heat and light. So the flame that you see is actually the reaction taking place. You're seeing the chemicals react when you see the flame. Example of that would be hydrogen gas reacting with oxygen gas to produce water vapor. Well, it depends on what you're doing. In certain applications, it does matter. So, I mean, right now we're just learning about the reaction types. Well, you would need to have oxygen gas for it to be combustion. So if you had oxygen solid, oxygen liquid, you would not have combustion. So that, in that case, yes, that would matter if this were gas or not. But that'd only be for oxygen that would matter in this situation. So this reaction takes place in rocket engines. Rockets burn hydrogen and oxygen in different tanks. And the result is water. Now it's a form of gas, but you can cool it down, you get water from it. And so this is a combustion reaction. Notice also this is synthesis too, because you are taking two things and making this into one. So this is also is synthesis. So a lot of reactions can be classified as more than one kind. And this would be an example of one where you classify as combustion and synthesis. It's both. Yeah.
So is water incredibly stable?
Yes, it is very stable. Yeah, because water is not really reactive. I mean, there's not. I mean, you can get it to react, but not that, especially in liquid form, it's not very reactive. And in gaseous form, it's more reactive. You need a very reactive chemical. So you can see water react with lithium, for example. You did this one before. Remember, you put lithium in water and it started to bubble up. So that's an example of water reacting with something. Another example would just be adding salt to water. The water breaks apart the salt molecules. That's a reaction. And so water can do things like that. It's usually not very violent. Usually it's a very calm reaction, but water can break apart salts and sugars. So that's the primary reaction we see with water. Okay, so that's synthesis as well as combustion. Now, you can burn natural gas, and that's CH4. Okay, so in this case, you have methane or natural gas, CH4, that's reacting with oxygen. And when that happens, you see a flame, and it's forming carbon dioxide gas and water vapor. Now, in this kind of reaction, this is called complete combustion, where you have these two products form. So if you have enough oxygen present and you're burning something, you're going to get a complete combustion reaction where you always get carbon dioxide and water form. So that's with enough oxygen. But if you decrease the amount of oxygen with oxygen deprivation, like in a chimney, for example, if there's not enough airflow in the chimney, or in your car where there's not enough oxygen sometimes to burn the gas, you're going to instead get carbon monoxide being produced. Yeah, if you had enough oxygen, then you would only get carbon dioxide produced. Now, we don't have a way to do that. We're not able to, but we have catalytic converters which can convert carbon monoxide into carbon dioxide. Yeah. How do you know whenever it actually is a combustion reaction? Do you mean like between this one and this one, or do you just mean combustion in general? Combustion in general would be reacting with O2. So if you have something reacting with O2, that's combustion. Do you need to have like O2 in? No, you don't. You just need to have it reacting with O2. So that's the only way we know it's combustion is if it reacts with O2. You wouldn't have a compound on the other side? Like instead of two compounds, why wouldn't these be together as one? It wouldn't be stable that way. There's no stable compound you can combine with hydrogen, oxygen, carbon. It just breaks into more stable compounds, and this is how they can rearrange in the most stable way. Yeah. What do you mean by deprivation? So that would be a condition where you don't have enough oxygen present. So that would be like in the candle flame you saw last week. Remember how it looked in the candle flame? The very center of the wick was dark. There is no flame present. Why was there no flame next to the wick? That's right. And so there's not enough oxygen in that area. And so with less oxygen present, you're going to have some reaction take place in certain situations. You might have carbon monoxide produced, or like a chimney, for example. If you don't open the flue, the top part that lets air come in, you're going to have more carbon monoxide buildup in the house. You might have heard about, when we had that winter storm this year, people actually died of carbon dioxide poisoning in their house because they had a fireplace going, or they were burning their natural gas and they didn't have enough airflow, and it built up. Now you can't smell carbon monoxide; it's odorless, so you don't know you're breathing it in until it's too late. So it's a very dangerous gas because carbon dioxide, you get a suffocating feeling. If you ever had a soda and you like had your nose over the bubbles and you breathe it in, it's really, really unpleasant. You feel like this choking feeling right away. And that's carbon dioxide. But carbon monoxide, you don't get that. You probably have all smelled car exhaust before. In car exhaust, you don't have the unpleasant feeling that you're breathing in carbon monoxide, but it doesn't smell well. Okay, that's not carbon monoxide you're smelling though, but it's carbon monoxide that you are inhaling is not unpleasant. You don't feel the choking sensation. Yeah.
So I heard another reason from the fireman who was working on this home that they had to convince many people not to bring their gas stove or their gas grills.
Yeah.
Grills into their house.
Yeah. I mean, because you think, okay, we need to warm up, we need a fire, and so you think, well, we're gonna make a fire in here, but if you don't have airflow, you're going to get a lot of carbon dioxide build up really, really fast. And I understand it was really cold in my house too. It got about 39 degrees in my house, and it's really cold, but you can die from bringing in your gas grill. Now, if you have even less oxygen, then you would have just carbon being produced, just carbon solid being produced. Does anybody know what that looks like? Like it's the ash you see on your chimney. Like it's the black soot. So if you see black soot present, that is a sign that you are burning with less oxygen than you need. That's also a sign you're producing carbon monoxide. So if you see soot from a flame, then you know you're producing carbon monoxide. And
Can that black also be produced from smoke?
well, sure, there is some in the smoke, but if you're seeing a lot of ash build up, then that's a sign that you have not enough oxygen present in the flame. But yeah, there definitely is some carbon in the smoke as well.
What is the other?
Okay, so that's these are incomplete combustions. These two are incomplete. This one would be complete. So complete combustion takes place with enough oxygen present, and you get carbon dioxide and H2O produced. With incomplete combustion, you don't have enough oxygen present, and you get different products. Okay, third reaction type we'll get to today, then I'll give you some homework to work on before class ends. The third reaction type, and there's 5 reactions we're going to talk about. Today we'll do 3, tomorrow we'll do the other 2. Decomposition is the third one. So what do you think this one would do? Decomposition? What does that mean? Breaks down. That's right. To decompose something, you break down, you have a compost pit at your house. What's the idea behind that? You're putting in, old food that breaks down, it creates soil and fertilizer. So to decompose. So decomposition, you have a single compound. You start with one compound and it breaks down into 2 or more elements. So a single compound breaks down into 2 or more things. Generically, it looks like this. You have compound AB separating into elements A and B. So you start with 1, you end with 2 or more. An example of that would be what happens in airbags in cars when they're deployed. In the car, you have sodium azide. It's NaN3, and it's pellets. When you have a car accident, the car sends a signal of electricity that breaks apart the sodium azide into sodium solid. Then it wouldn't work. Sometimes that does happen. Sometimes the airbags don't work. It's not, well, no, I mean, because we didn't have airbags until the mid 90s. And so, no, that's not true. No, people drove a lot faster than 20. I mean, now definitely we did have lower speed limits back then. That's definitely true. When I grew up, 55 miles per hour was our speed limit, and that's as fast as you could go. But that was because Jimmy Carter in the 70s was concerned about oil and fossil fuels being produced, and it wasn't so much about car safety as more as environmental concerns. And it just stayed that way from the 70s to the 90s. Then they eventually raised the speed limit to 70 miles per hour in the 90s, late 90s, because they're used to it. But no, I mean, you can still survive a car accident without airbags being deployed. Of course, it's going to help your survival rate if you have airbags deployed, but it doesn't mean you're going to die. Your seatbelt on, and you have a new car, you have a good chance of surviving because the new cars hold up really well. But no, I mean, people, didn't have seatbelts, people didn't have airbags, and they drove cars, and most people survived. But yeah, sometimes airbags just don't work, and it's pretty rare that would happen because generally it would deploy before the wire is split. It's going to sense the accident happening before it gets to that point where it destroys the wire. But of course, it's definitely a positive. It's just nowadays with the cars, they can sense oncoming collisions, and they can actually be proactive before you actually get the collision. Yeah, they have radars. They have, and so. Oh wait, I'm sorry. I wrote down the wrong thing. That should not be H2O gas. I was looking at a different reaction. That should be nitrogen gas. Sorry about that. Cross out the H2O gas. I was looking at the wrong thing. You get nitrogen gas produced in that reaction. And that's what your airbag fills up with. It's nitrogen gas. So it has to be a very fast reaction. It happens in less than a second. And your airbag is set to basically, ignite this so that it can break apart into sodium, which then decomposes very quickly. Sodium's not very stable. And then nitrogen gas, which fills up your bag. So that's decomposition. You start with one thing, then it breaks apart the elements. So usually what you're going to do in decomposition is you're going to break apart each element into its own thing. Not always though. You could have something like this where you have baking soda, sodium bicarbonate. And what would happen here is you would not have just sodium, hydrogen, carbon, and oxygen form. You actually would have, so you're saying NaH and then carbonate. So if you had a solution, that could definitely happen. So yeah, I mean, if you were just in a solution, it's possible you'd have that happen. This would not be as common, but that if you had it in water, that could certainly happen. So a more common one would be this actually, Na2CO3 along with water and carbon dioxide. That'd be a more common. Well, we have to balance it. We have to go back and, I haven't balanced it yet, but that would be a more common decomposition, which all it would really mean is that you are getting several products from one. And so you can make something like that happen where it's not just separated by elements. Because sodium on its own is very unstable. And so you wouldn't see generally sodium by itself. Now you see it in this reaction, but it only stays away for short amount of time, it's going to convert very quickly into sodium nitrate, or sorry, sodium oxide. It won't stay sodium very long, just too reactive. Same thing here. The sodium on its own is going to separate very, very quickly, but it's going to recombine with carbon and oxygen to make sodium carbonate, along with water and carbon dioxide. So 20 minutes to go. In your book, let's see what page that's on. On page 291, do those questions in 14 through 17, and then go on to the next page and do up to 20. So on page 291, do 14 through 17, and go on to the next page and do up to 20. Do you want to? Oh, yeah, yeah.